Hello all. In today's lecture, we are going to see 2-bit magnitude comparator. In a previous lecture, we saw about how to design a 1-bit magnitude comparator. In today's lecture, we are going to see how to design a 2-bit magnitude comparator using combinational logic circuit. You very well know when it comes to designing any circuit using combinational logic circuit, what are the 4 basic steps that you'll have to follow? First, you have to draw your block diagram, followed by you have to draw a truth table. After drawing the truth table, from the output of your truth table, you have to derive your Boolean expression, for which you will be requiring your K-map. And after finding the Boolean expression using K-map, what is the final step? Designing the circuit using logic gates. Now, let's see how to draw our block diagram. How do you draw a block diagram? For a 2-bit magnitude comparator, let this be my magnitude comparator. And let my inputs be A1, A0 and the other two inputs be B1, B0. Clear? This is one 2-bit pair and this is another 2-bit pair. Clear? Now, you know magnitude comparator has got 3 outputs. One is A less than B, another is A greater than B, and another one is A equal to B. Clear? Now, we are done with the block diagram. What is the next step? We have to draw a truth table. Fine. Let's see how to draw a truth table here. Now, what are my inputs? A1, A0, B1 and B0 are my inputs. Clear? Now, what are my outputs? A less than B, A greater than B, A less than B, A greater than B and A equal to B. These 3 are my outputs. Now, I've got 4 bits. How many combinations will be requiring? Check on your inputs. How many input bits you have got? You have got 4 bits. A1, A0, B1, B0. You have got 4 bits. So, if you have 4 bits, how many input combinations you will be getting? If the number of inputs is equal to 4, n is equal to 4. So, number of combinations it will be? It's based on the formula 2 power n, which is 2 power 4, which is nothing but 16. So, I'll be getting combinations from 0 to 50. Clear? Write down the combinations. It is 0, 0, 0, 0. Why did I put a line here? This is something like for my input combinations when A1 and A0, when it is 0, 0, I'll be getting 4 different combinations for my B1 and B0. In a similar way, for my input A1 and A0, when it is 0 and 1, for this combination again, I'll be getting 4 combinations for B1 and B0. That is 0, 0, 0, 1, 1, 0 and 1, 1. Clear? For all this 4 combination, my input A1 and A0 is 0, 1. Is it clear? Similar way, for the other combination, when my input A1 and A0 is 1 and 0. For this particular combination again, I'll be getting 4 input combinations for B1 and B0. That is 0, 0, 0, 1, 1, 0 and 1, 1. For all the 4 combinations, my input A1 and A0 will be 1, 0. Is it clear? Now, the other possible last combination is 1 and 1. When my input A1 and A0 is 1 and 1, for this particular combination again, I'll be getting 4 different combinations for B1 and B0. That is 0, 0, 0, 1, 1, 0 and 1, 1. For all these 4 combinations, my input A1 and A0 will be 1, 1. Is it clear? Let me give the decimal number so that you'll be able to understand it better. This is 0, 0, 0, 0. It is 0, 0, 0, 0, 1. It is 1, 0, 0, 1, 0. It is 2. I'm writing the decimal numbers here. 0, 0, 1, 1. What is this? This is number 3. 0, 1, 0, 0. It is number 4. 0, 1, 0, 1. It is number 5. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Clear? I've got all the 16 combinations for 4 bits. Is it clear? Now, how do we do the comparison? We are done with our inputs. We have written all the combinations for input. Now we have to find your output. How do you find your output? Same condition as we did for 1-bit magnitude comparator. Check for whether your combinations for on your input, whether it is A less than B, or whether it is A greater than B, or whether it is A equal to B. If any of this particular condition is getting true, against that particular condition you have to mention 1. For the other remaining conditions you have to mention 0. Is that clear? The same procedure as we did it for 1-bit magnitude comparator, you are going to repeat the same here. If you have not seen that magnitude comparator, I'll give the link of it in the description. Kindly refer to it so that you'll understand it more clearly if you watch that video. Clear? Now, let's take this first input combination. Here, A1 and A0, this entire thing, I'll assume it as A input. And this B1 and B0, I'll assume it as B input. Clear? 0 and 0. What is the equivalent decimal for it? Assume the decimal number so that it will be easy for you to do the comparison. What is the decimal for this particular combination of A? For this entire combination of A, that is A1 and A0, my A is equal to 0. Right? Similarly, for this particular combination, B is, for this particular combination, it is 0. For this combination, B equal to 1. For this combination, B equal to 2. For this combination, B equal to 2. I am just considering only this portion for B. Is it clear? Assume the decimal number and do the comparison so that it will be very easy for you to fill the output. Clear? This combination A equal to 0. How did I assume? I have taken A1 and A0. Both the combination together. Assume these two numbers as a single number. 0, 0. What is the equivalent decimal for 0, 0? It is 0. That is what I have written here. So for this entire 4 bits, my A1 and A0, it is 0, 0. So together I have taken A as 0 for this particular block alone. Clear? And coming to B, I'm going to take only this 4 combinations. For this 4 combinations, what is the output of 0, 0 in your decimal? It is 0. 0, 1 in your decimal, it is 1. 1, 0 in your decimal, it is 2. 1, 1 in your decimal, it is 3. Let's find the output for this particular block alone right now. And then we'll move with the remaining blocks. I'm assuming this 4 numbers as a single block. Clear? Now, do the comparison. A is 0 here, B is again 0 here. For the first bit I'm taking for the first bit. Check on the numbers. A is 0, B is 0. Both the numbers are same, so I'll be mentioning 1. When both the numbers are same, it means A is equal to B. That's why against A equal to B, I've put a 1. Clear? And for the other 2 conditions, I'll be mentioning 0. At a time, only one condition can get satisfied. 2 or more conditions cannot get satisfied at the same time. Here, of the 3 conditions, A equal to 0, B equal to 0, which means A is equal to B. So only this particular condition is getting true. So I have mentioned 1 here. Is it clear? Now go for the next combination. Here A is equal to 0, right? What is B? 0, 1. B is equal to 1. A1, A0. B1, B0. 0, 0. For this particular condition, A is equal to 0, 0. B is what? B is 0 and 1. What is the equivalent decimal? 0, 0. Equivalent decimal is 0. The equivalent decimal for 0, 1, it is 1. Which means A is equal to 0 and B is equal to 1. We have to represent it in terms of A. So, this is nothing but A less than B. Is the condition getting true here? So, against A less than B, you will put 1. And for the other numbers, you will mention 0. Is it clear how to fill the magnitude comparator table? Now, let's go with the next combination. A is what? A1, A0, 0, 0. What is B1 and B0? B1 and B0 is 1 and 0. Correct? So, what is the equivalent decimal for this? It is 0. Equivalent decimal for 1 and 0, it is 2. Here A is 0 and here B is 2. What does it mean? A is less than B. So, for this particular condition, you have to mention 1. And for the other conditions, you will be mentioning 0. Is it clear? Check for the other condition. Without writing orally, you can tell me here. A is 0, B is 3. What does it mean? When A equal to 0 and B equal to 3. What does it mean? A is less than B. So, against A less than B, I'll put a 1. For the other conditions, I'll put a 0. Is that clear? Now, we are done with this entire block. Check for this particular block now. For this particular block, A1 and A0, it is 0 and 1. It is common throughout. So, what is the equivalent decimal for 0 and 1 combination? It is 1. Clear? Now, for this particular block, give me the equivalent decimal. 0, 0, it is what? It is 0. 0, 1, it is what? It is 1. 1, 0 is what? It is 2. 1, 1 is what? Equivalent decimal, it is 3. Now do the comparison for this particular term. Here A is 1 and B is 0. In terms of A, we have to see. When A is 1 and B is 0, what does it mean? It means A is greater than B. What is A? A equal to 1 and B equal to 0. What does it mean? A is obviously greater than B. So wherever A is greater than B, against that you will put a 1. And for the other combinations, you will mention 0. Is it clear? Now, check for the other number. Here it is 0, 1. Here it is 0, 1. So, what is the equivalent decimal here? For A, it is 1. And for B, again, it is 1. A is 1. And B, again, it is 1. What does it mean? Both are equal. So, against A equal to B, put a 1. And for the other combinations, you have to put 0. Is it clear? Now, check for this particular combination. For this particular combination, A is 1. And B is 2. A is 1 and B is 2. What does it mean? A is less than B. Right? So wherever A is less than B, against that you'll put a 1. And for the other conditions, you'll mention 0. Is it clear? For this particular combination. Here A is 1 and B is 3. A is 1 and B is 3. What does it mean? It means A is less than B. So wherever A is less than B, you'll put a 1 and for the other conditions, you'll mention it as 0. Is it clear? Now, do for this particular block. What is the value of A? By looking at this only, you should be able to tell now. What is the value of A for this entire block? For this entire block, A1 and A0 it is common. Right? And what is the equivalent decimal for 1 and 0? 1 and 0 equivalent decimal is number 2. Right? So, for this entire block, my A is equal to 2. Clear? Now, for this particular, this is my B block. Right? Now, for the B block, what is the decimal for this? It is 0. For this particular number, B is 1. Here, B is 2. And for this number, B is 3. Now, do the comparison. Here, A is 2. Here, B is 0. Here, A is 2 and B is 0. For the first combination, I am taking. Here, 1, 0 equivalent decimal for 1 and 0 is 2. Here, the equivalent decimal for 1 and 0 and 0, it is 0. So, it means A is equal to 2 and B is equal to 0. What does it mean in terms of A? A is greater than B. Right? So, wherever A is greater than B, here you have to put 1. And for the other conditions, you will mention 0. Is it clear? Now, check for the next combination. Here it is 1, 0 and here it is 0, 1. A1, A0, B1, B0. A1, A0 is what? 1 and 0. B1 and B0 is what? 0 and 1. So what is the equivalent decimal for this? It is number 2. Equivalent decimal for it, it is number 1. What does it mean? A equal to 2 and B equal to 1. So in terms of A, when you speak, A is greater than B. Right? So against A greater than B, you will mention 1 and for the other combinations, you will mention 0. Is it clear? Now, come for the next combination. Here 1, 0 and 1, 0. Both are same. Here again 1, 0, here again 1, 0. Both are 2 and 2. So it is equal. So I'll put a 1 here and I'll put 0 here. Clear? Now, what is the last combination for this particular block? Here A is equal to 2. Here B is equal to 1 and 1. The output for this it is number 3. Here it is 2 and here it is 3. So, in terms of A when you speak, A equal to 2, B equal to 3. In terms of A when you speak, A is less than B. Right? So, A less than B. Where is A less than B? Here you will mention 1 and for the other conditions you will mention 0. Is it clear how to fill the block? Now, for the last combination, without even doing all this mapping, tell me orally. 1 and 1. What is the equivalent for this in decimal? For this entire block, what is the equivalent? A equal to 3. Right. For this entire block, A is going to be 3. And here you very well know what is the combination of B. Here B is 0, B equal to 1, B equal to 2, B equal to 3. Now, by looking at this only, tell me the output. Here A is equal to 3, here B is equal to 0. So, what does it mean in terms of A? A greater than B. Right? So, where is A greater than B? Put a 1 here, put a 0 here. Here it is 3, here it is 0. So, 3 is greater than 0. Right? For the second combination, here it is 3, here it is 1. Which means A is greater than B again, 3 is greater than 1. So, wherever 3, so A greater than B, so you put a 1 here. Clear? For the next combination, here it is 1, 1, which is number 3. Here 1, 0, equivalent for it is number 2. So, 3 is greater than 2. Again, A is greater than B here. Now, for the last combination, here again it is 1, 1, here again it is 1, 1. What does it mean? Here again the equivalent decimal is number 3, here again equivalent decimal is number 3, which means A is equal to B. So, wherever A is equal to B, put a 1 and for the other conditions, you will put a 0. Clear how to draw the truth table? It is very simple. Just give the input combinations. How many combinations? Based on the number of bits, you will find out how many combinations you will be recurring. For 4 bits, you will be having 16 combinations. That is from 0 to 15. So, you will write all the 16 combinations here. Now, after that, you have to take, why it is called 2-bit? Because A1, A0, this is 1 2-bit and B1 and B0, this is another combination for 2-bit. You are going to do a comparison between 2 bits. Right? You are going to do a comparison between this particular 2-bit and this particular 2-bit. Clear? That is why it is called as 2-bit comparison. Now, how do you do the comparison? Easy method I have told you. Take the equivalent decimal for it and then try to do the comparison. Wherever the condition is getting satisfied, against that particular condition, you will mark a 1 and the other conditions, you will mention 0. Clear? Take it block by block so that it will be easy for you to fill out your output. Clear? Now, we are done with our output. What is the next step? You have to find out a Boolean expression. How do you find a Boolean expression? You have to take your output to your K-map, simplify, and then you'll be finding a Boolean expression. Clear? How many outputs you have got? You have got 3 outputs. A less than B, A greater than B, and A equal to B. So, how many K-maps you'll be requiring? You'll be requiring 3 K-maps. Clear? And which variable K-map you'll be requiring? How many input bits we have got? 4 input bits. So, which variable K-map you'll be using? 4 variable K-map. Clear? Now, let's do the K-map. By now, I assume you are clear with how to do the K-map, how to position the numbers, how to do the numbering and all. If you still have any doubt, I'll give the link of my K-map lecture in the description box. Kindly refer to it and then come here so that it will be easy for you to understand. Clear? Now, this is for A less than B. Clear? For A less than B. Where is A less than B? How do you position the numbers in the K-map for A less than B? Wherever you have got your output as 1. Check for the corresponding decimal number, and against that particular decimal number which has got your output as 1, position them as number 1 in your K-map. Clear? Let's solve it so that it will be easy for you to understand it better. Now, check for A less than B. Where all have you got output as 1? You have got an output 1 here, you have got an output 1 here, you have got an output 1 here, here, and then here. Check for the equivalent decimal number. Here against 1 you have an output 1. So against, these are my decimal numbers. Fine, these are my decimal numbers and I've marked the decimal numbers here. So against this particular decimal number, wherever you have got your output as 1, you have to position 1. By default, it is all only SOP. Clear? Now, for this particular one, what is the equivalent decimal? It is number 1. So against 1, I'll mark 1. Clear? Where do you have your next output as 1? Here. What is the equivalent decimal number? Number 2. So against 2, I'll position 1. Clear? Where's your next output? Here. Against here you have got a 1. So what is the equivalent decimal number? It is number 3. So against 3 again, I'll position 1. Clear? Wherever you have got your output as 1, check for the equivalent decimal number. And against that particular decimal number, you have to position 1. Is it clear? Now, check for the other numbers. Here you have got a 1. This is corresponding to decimal number 6. Again 6, I'll position 1. Here again you have got a 1, which is corresponding to the decimal number 7. So against 7, you mark a 1. Clear? And then coming here, against 11 you have got 1. So against 11 you will position 1. Is it clear how to position the numbers inside the K-map? After positioning, what is the next step? You have to do the mapping. How do you do the mapping? I found a quad here. I've got a pair here and then another pair. Now, after doing the mapping, what is the next step? You have to find out a Boolean expression. How do you find out? Let me take this particular quad. For this particular quad, check vertically as well as horizontally. Whichever is the common term, you have to take out only that common term for writing a minterm. Clear? Now, for this particular quad, check vertically. Which is common? Only the first digit is common. The second digit, here it is 0, here it is 1. It is varying. So, I cannot take the second digit. Whereas the first digit, here it is 0, here again it is 0. Only the first digit is common. The first digit corresponds to A1 and the second digit corresponds to A0. Clear? And by default, you very well know in SOP, 0 is represented with complement and 1 is represented with an actual variable. Right? Here, since it is 0, you will be representing A1 as its complement. So, it will be A1 bar. Clear? You have just written only the vertical part. You have to write your horizontal also to complete that particular minterm. Now, check on your horizontal part. Which is common here? Only the first digit is common. Right? And what is the first digit corresponding to? First digit corresponds to B1. Since it is 1, you will be mentioning it directly. So, first digit corresponds to B1. So, I will be writing B1 directly. Is it clear? Now, coming to your next minterm. Let me take this particular pair. For this particular pair, A1 and A0 both are common. Right? And since it is 0 and 0 here, 0 will be represented with a complement. So, I will be writing it as A1 bar, A0 bar. Is it clear? Now, for this particular pair, check horizontally. Which is common here? Only the second digit is common. Second digit corresponds to B0. So, I'll write B0. Clear? Now, there is another pair here. Check for this particular pair. For this particular pair, on your vertical, which is common? My second digit is common. Clear? And second digit corresponds to A0. And since it is in 0, how do you represent 0? 0 will be represented as a complement. So, it is A0 bar and on your horizontal, This 1 and 1 is common to both these two terms. Right? And so 1 and 1, how can you write? It is B1, B0. Clear? This is the Boolean expression for A less than B. Clear? Can we do any simplification here? No. There is no possible simplification. So we can leave it as such. Clear? How to write the Boolean expression for A less than B? We have just done with A less than B. In a similar way, we have to find the Boolean expression output for A greater than B and A equal to B as well. Clear? Now, let's do it for A greater than B. A1, A0, B1, B0. Now, this is your K-map for A greater than B. How do you position the numbers inside the K-map for A greater than B? For that, take A greater than B. We are taking only this particular output. How do you position the numbers? Same process. Check for your output. Wherever you have got 1 in your output, check for the corresponding decimal number. For the decimal number which has got your output as 1, against that particular decimal number, you will position 1 in your K-map. Clear? Now, for A greater than B, this is for A greater than B K-map. For this particular K-map, check on your output. Where all have you got 1? You have got 1 here. So 1, this particular 1, it is corresponding to number 4. So against 4, position 1. Clear? Now, where all you have 1, you have got 1 here. And this is corresponding to number 8. So against 8, position 1. Clear? Here again you have got a 1. This corresponds to number 9. So against 9, put a 1. Now, here you have got 1. This corresponds to number 12. And this is to number 13. This is to number 14. So 12, 13, 14. 12, 13 and 14, I'll position 1. Clear? Wherever you have got your output as 1, check for the corresponding decimal number. And against that particular decimal number, you have to position 1 in your K-map. Is that clear? Now, do the mapping. Here, all these 4 numbers, I can do one mapping. These 2 numbers, I can do another mapping. And these 2 numbers, I can do another mapping. Clear? Now, give me the expression A greater than B. What is A greater than B? For this particular quad, check vertically as well as horizontally, whichever is common. For vertically, only the first term is common. What the first term corresponds to? It corresponds to A1. Clear? And now check horizontally, which is common here for this particular quad. Here, only the first term is common. Here it is 0, here it is 0. And digit corresponds to B1. And since it is in 0, I'll put a bar. Clear? Now, check for the second min term. I'm taking this particular pair. For this particular pair, on your vertical, which is common, only my second digit is common. Second digit corresponds to A0. Clear? And on your vertical, this 0 and 0 is common to both the numbers inside this particular bubble. So I'll write both. It is 0, B1 and B0. And B1 and B0, it is mentioned as 0 and 0. So how do I represent? I'll represent them with a bar. Clear? Now, what is the next min term? I'm taking this particular min term, the corner pairs. For this particular pair, on your vertical, which is common, A1. Both are 1 and 1. And 1 and 1 is common to both the terms. So this corresponds to A1 and A0. Clear? And check horizontally again, which is common. My first digit, it is varying here. Here it is 0, here it is 1. So I cannot take that. Take only the second digit. Here it is 0, here it is 0. The second digit is matching. Clear? What does the second digit corresponds to? It corresponds to B0. But since it is 0, I'll be mentioning that with a bar. Clear? See if you can do any simplification here. No, I can't do any simplification. So this is going to be my final Boolean expression for A greater than B. Clear? In a similar way, we have to find the equation for A equal to B as well. Clear? Now, let's do it for A equal to B. This is for A equal to B. Now, how do you position the numbers inside K-map? The same procedure. Wherever you have got your output as 1, check for the corresponding decimal number. And against that particular decimal number, you have to position 1. Clear? We are going to do it for A equal to B. For A equal to B K-map. Clear? Now, check where all you have got 1. You have got 1 here, you have got 1 here, 1 here, and 1 here. You have got 1 in only 4 places. Here, this is corresponds to number 0. So, here you have got 1. Here, this corresponds to number 5. So, against 5 you have got 1. Here, this corresponds to number 10. So, against 10 you have got 1. And the last digit corresponds to number 15. So, you've got here 1 here. Clear? Now, do the mapping. Can we do any mapping here? No, we have to go only for single digit grouping. Right? So, give me the equation. This is nothing but for this first term. What is this? It is A1, A0, A1 bar, A0 bar, B1 bar, B0 bar. I told you for single digit grouping, you will not be going for any common term. Only if there is a grouping of either pair or quad or an octave grouping, you will take out the common terms for writing your minterm. In case, if there is a single digit grouping, as in this case, then all the terms on your vertical as well as on horizontal for that particular bubble, and then you will write everything for your minterm. For this particular bubble, what is there in my vertical? It is A1, A0. Both are in 0, 0. So I have to take a complement of it. So I have taken A1 bar, A0 bar. And on your horizontal, here it is B1 bar, B0 bar. So I have taken all the terms. Clear? Now, coming to the next term. This particular bubble, it is A1 bar, A0, B1 bar, B0. Clear? And for this particular bubble, it is A1, A0, B1, B0. And for this particular bubble, it is A1, A0 bar, B1, B0 bar. Clear? Try to simplify this equation now. Can we take any terms outside? Yes, A1 bar, A0 bar, we can take it here. On these two terms, I'm going to take A1 bar and B1 bar. So A1 bar, B1 bar, I'm taking it out. So it will be A0 bar, B0 bar plus A0, B0. This is for the first two terms alone I have taken. In a similar way, for the remaining, for the next third and fourth term, which is common here, A1, B1 is common. So I'm going to take A1, B1 outside and it will be A0, B0 plus A0 bar, B0 bar. Clear? Which gate is this term inside your bracket representing? It is nothing but my XNOR gate. So try to replace it. A1 bar, B1 bar. The terms inside my bracket is my XNOR gate. How do you represent XNOR gate? You'll be representing XNOR gate like this. Clear? And similarly, for this particular term, here it is A1, B1 into, here again it is XNOR gate combination. So I'll be mentioning like this. Now, these two terms are common. So I'm going to take these two terms outside. And when I take A0, XNOR B0 outside, then it will become A1 bar, B1 bar plus A1, B1. Right? From these two terms, I'm going to take A0, XNOR B0 outside. The other terms I have just written it like that. Now, how is this term representing? This again is my XNOR gate. Right? So can I write it like A? This is one term. For this entire term, I'm going to write it as A1 XNOR B1. Clear? This is the final expression for A equal to B output. Understood? Now, we have found the Boolean expression for A greater than B, A less than B and A equal to B. So, what is the final step in the design procedure after finding the Boolean expression? You have to design the circuit using logic gates. Clear? Now, let's see how to design the circuit using logic gates. Is it clear? Take all your inputs. Let this be A1 and the complement of it. I'm going to take A0, complement of it, B1, I'm going to take a complement of it, and B0, and I'm going to take a complement of it. Clear? Now, let's design A greater than B first. How do you design? What are the terms? It is A1, B1 bar. The complemented output will be for this particular input. A1 is here. If I feed it inside a NOT gate, what is the output of my NOT gate? It is A1 bar. Here it is A0 bar. Here it is B1 bar. Here it becomes B0 bar. Clear? Now, for the first minterm, what is this? Now, for the first minterm, it is A1, B1 bar. So, take the lead from A1. And where is your B1 bar? B1 bar is here. So, these two terms I have got to take. And what they have done here, it is a product term. So, put them inside a AND gate. What is the output of it? It is A1, B1 bar. Clear? And now, what is the second minterm? It is A0. So, A0. From A0, I'll take a lead. Here, B1 bar, B0 bar. B1 bar and B0 bar. All these three, I'm going to feed it. This is a product term. So, I'm going to feed it inside an AND gate. The output of it will be A0, B1 bar, B0 bar. Clear? And what is my final term? It is A1, A0, B0 bar. So, A1, I'll take the lead from here. A0, I'll take the lead from here. And then B0 bar. B0 bar, I'll take the lead from here. So, all these terms, I can take it. What is the output? It is A1, A0, B0 bar. all the three minterms, what have they done here? They have summed it up. So the output of all these three minterms I'll be taking and then I'll be feeding it inside my NOR gate. What is the output of this? This is nothing but A greater than B. Is it clear? This is how you'll be designing A greater than B. Is it clear? In a similar way, you have to design A less than B as well. In a similar way, you have to design A less than B as well. Clear? Now, let's see how to design A less than B. What is A less than B? This is my output for A less than B. Clear? Now, what is A less than B? What is the first term? It is A1 bar B1. Where is A1? A1 bar and B1. Take the lead from B1. B1 is here. These two terms, what they have done? They have done a product. So I'll be feeding it inside my AND gate. What is the output of it? It is A1 bar B1. Clear? Now take the second minterm. What is this? It is A1 bar A0 bar B1. A1 bar A0 bar A0 bar and B0. Where is B0? B0 is here. All the three terms I'll be taking it here. What is the output? It is A1 bar, A0 bar and B0. Clear? A1 bar and what is the second lead? It is A0 bar and a third lead corresponds to B0. Is it clear? Now, what is the final minterm? It is A0 bar, B1 and B0. A0 bar, where is A0 bar? A0 bar is here. So, take the lead from A0 bar. Clear? And it is B1 and B0. Where is B1? B1 corresponds to this particular line. So, take a lead from here. Clear? Now, next term it is B0. So, where is B0? B0 it is here. All the three, put them inside an AND gate. So, what is the output of this? This is what? This is A0 bar. What is the input? Here it is B1 and this lead corresponds to B0. Clear? Now, I'm done with all the three minterms. What have they done to all the three minterms? They have summed it up. So, the output of all these three minterms I'll be taking and then I'll be feeding it inside my OR gate. So, what is the output of it? It is nothing but A less than B. Is it clear how to design the circuit for A greater than B and A less than B? Now, we have to design the circuit for A equal to B. This is my A equal to B output. Right? So, what is A equal to B? A equal to B output is nothing but A naught, X naught, B naught. A naught is where? A naught is here. So, I'll take the lead from here and B naught. B naught is where? B naught is here. So, I'll take the lead from here. These two, I'll be sending them inside a X naught gate. Clear? What is the output of this? This is nothing but A naught, X naught, B naught. Now, what is the second term? It is A1, X naught, B1. A1 is where? A1 is here. So, let me take the lead from here. Clear? And where is B1? B1 is here. So, let me take the lead from here. So, send them inside an X naught gate. So, this is A1, X naught, B1. What they have done, A1, the first term and the second term, what they have done? There is a product. They have done a product here. So, for a product, which gate you will be using? You will be using an AND gate. So, these two output I will be taking and then I will be feeding it inside an AND gate. So, this is nothing but A equal to B. Is it clear how to design the circuit for A greater than B, A less than B and A equal to B? This is how you will be designing your 2-bit magnitude comparator. Understand? Let's sum it up. What did we do for a 2-bit magnitude comparator? First step in the design procedure, we have to draw a block diagram. After drawing a block diagram, we have to draw a truth table. Fine. For your truth table, based on the input, how many bits are there? Based on that, you will decide on how many combinations you will be taking. Clear? After finding the combinations, you have to fill your output. How do you fill your output? That is based on the condition. You have to check for the condition. Whichever condition is getting satisfied, against that particular condition, you will be mentioning 1. For the other condition, which is getting false, for that you will be mentioning 0. After filling the output for all the three conditions, that is for A less than B, A equal to B, A greater than B. What is the next step? You have to find your Boolean expression. But how do you find the Boolean expression? For that, you will be taking your output to your K-map, do the simplification and then you will be finding a Boolean expression. For taking it to the K-map, what you have to do? You have to take your output. Wherever you are finding 1 in your output, check for the corresponding decimal number, and against that particular decimal number, you'll be mentioning 1 in your K-map. Clear? After positioning the numbers, you do a mapping, take out the common terms, write the min terms, and then you'll be finding a Boolean expression. Clear? In a similar way, you have to do for all the three outputs. That is for A less than B, A greater than B, and A equal to B. Clear? After finding the Boolean expression, what is the final step? Based on a Boolean expressions that you have got, you have to design the circuit using logic gates. Clear? And this is the final design of a 2-bit magnitude comparator using combinational logic circuit. Is it clear? I hope you are clear with this lecture. If you find my lectures useful and informative, please do like, share and subscribe to my channel. Thank you.